In many situations, the object being launched is not launched horizontally. It's launched at an angle. Now, sometimes when it comes back down, it is not symmetrical like this picture is showing. But this is an important application or case of projectile motion that we're going to discuss in this video. From just the initial velocity and the angle at which an object is launched or kicked, we can find how much time it will be in the air, how far the object will travel along the ground horizontally, and how high it'll go at its maximum point. To understand this, we do need to make sure we remember how to deal with something that has been thrown straight up in the air. Recall that if it takes 3 seconds for something to reach its peak, it's going to take another 3 seconds for it to come back down, and it's going to follow the same exact path on the way back down. Everything, again, is going to be very symmetrical. We had a few ways of finding how much time it takes to go up and down. Of course, this diagram shows the time, but if instead we had been given the initial speed, in this case as being 30 meters per second, we would have a number of different options of how to find the time in the air. We could use our velocity equation and recognize that the speed is the same when it leaves the ground and when it comes back down. It's just pointed in the opposite direction. And so we would put a negative 30 and a positive 30 into our equation. Or we could split the motion in half and just think that at the top, the speed will be 0. And so we could figure out how much time it takes sort of the object to run out of speed. And from this equation or situation, we would have found that t was 3 seconds, and then we would have doubled it to get 6 seconds. Or we can focus on the fact that it starts and ends at the exact same height above the ground. There's no difference in the beginning and the ending positions. And so we could set the delta x or the delta y as 0 and solve from there to get our time. And I just noticed there's a mistake in here. There should be a 1/2 right in here. Let me see if I can change that real quickly. Yes, I can. Okay, so there should be a 1/2 in that equation. Now, if the object is not only moving up and down, but it's also moving across, we can combine those two types of motion to describe the parabolic path that we see when something has been thrown in the air at an angle. When we switch to the horizontal direction, remember that there are no forces pushing or pulling the object in that direction. Once the object is released and it's up in the air, only gravity affects it, and that's just a downward force. And so the horizontal speed would remain the same. So we might picture that as this sort of dot diagram is indicating. If we put the two situations together, the up and down motion that's controlled by gravity, shown by the red dots, and the horizontal motion that doesn't change, that's shown by the blue dots, if we kind of map out second by second where the object would be, we can see where that curve comes from, where the parabola shape comes from the trajectory. So the key thing when we're looking at a problem is to separate the situation into the horizontal motion and the vertical motion, keep everything separated, and then recognize that time is something that we're going to be able to sort of reuse in both directions. Let's take a look at an example of how this might play out. All right, so in this situation, this baseball has been thrown at 18 meters per second, but not straight up and not horizontally. It's been thrown at an angle. So we need to think about how does that fit into our understanding of projectile motion. First of all, it might be a good idea to sort of sketch out what that looks like. 18 meters per second could be represented with a vector arrow, and we would point it 50 degrees from horizontal. Now, that's not the actual direction the object continues in, because remember that gravity will immediately be affecting its motion as soon as it's released. And so it won't really follow that red line. It will follow a parabolic path. And so everything we have used before about symmetrical motions and so forth, and about splitting up the x and y directions, we're going to have to apply that in this situation. So we'll go ahead and take a look at the horizontal and the vertical values. What's kind of crazy about this particular problem is none of the information that's given is actually in the x or the y direction. It's all at an angle. So the first thing we need to do is take this 18 meters per second and break it apart. We're going to think of that red arrow as the hypotenuse of a triangle. And we're going to need to find this piece here, which is in the x direction, and this piece here, which is in the y direction. These will be our initial velocities in each of these directions, and so then we'll be able to kind of organize our thoughts. So what we would do here is to set up a trig function to find the v sub o in the x direction. We could say that the cosine of 50 is equal to the adjacent side, which is the v sub x sub o, divided by the 18. And we would then end up multiplying both sides of the equation by 18, so 18 times the cosine of 50. That would give us our v sub o in the x direction, 11.57. But then we'd also want to look in the y direction, in the vertical direction. And in this case, we would use the cosine. So, I'm sorry, the sine. We just use the cosine. The sine of 50, what's going on with my page here? The sine of 50 is going to equal everything in the y direction, the v sub o in the y direction, divided by 18. Okay, and we'll organize that on this side of our chart. So this initial velocity is going to be 13.79 meters per second. Okay, so you can see right away this is different than the previous problems because there's a v sub o in both directions. Now, what are some other things that we know? Well, we know that in the vertical direction, our acceleration is going to be -10. And then we know that in the horizontal direction, because gravity doesn't point that way, and there's nothing pushing the object forward while it's in the air, this acceleration is just 0. All right, so what can we do with this? We can remember that when something goes up and it comes back down again, that the speed is going to be the same at the top and the bottom. Not the speed in the x direction, that just stays constant, but the speed in the y direction. So what we'll start with here is to say that v is equal to v sub o plus at over here. Just like we did to find time when we threw something straight up in the air. But we're going to use this 13.79 instead. We're going to stick with things just in the vertical direction. So we would launch it at 13.79, and the acceleration would be -10, and when it comes back down again, it's still traveling, or it's again traveling at 13.79, but now in the negative direction. Okay, and so now we could determine our time, and we would go through and do our algebra, and you would find that the time is 2.76 seconds. Again, that's the time to go up and to come back down again. So that's the first part of our question or our problem. Secondly, we're asked to figure out how far horizontally it travels. So now we'll switch gears and we'll use the horizontal information. We're looking for a distance, so we're going to have to use the distance formula. So delta x is going to be v sub ot plus 1/2 at squared. And again, now we're looking at this horizontal direction. Our acceleration is 0, so that means this whole term is going to be 0. and we're just thinking that distance is this horizontal velocity times time. So that would be 11.57 meters per second times our time of 2.76 seconds. We get a horizontal distance, what sometimes is called the range, of 31.9 meters. All right, almost done. Part C, what is the maximum height reached by the ball? I'm going to switch colors here so you can definitely see these calculations. So maximum height, that is a vertical idea. So we're going to be going back to this side of our situation here. Let me kind of extend my chart over here. I'm looking for a distance again. So I would use my delta x, or again I like to call it delta y, v sub ot plus 1/2 at squared. Start with that basic equation. Okay, so what do I got to think about? Well, I'm only going halfway through the motion. The maximum height does not happen at this time. It happens halfway through that time. So I would want to take 2.76 and divide it by 2. That gives me the time just to the peak. 1.38 seconds. That's a 3. It does not look like a 3 at all. All right, so that's what I'm going to plug into my equation to find that vertical height. I'm just sticking with this side of the setup here, only using vertical numbers. So 13.79 times my time of 1.38. Make sure I put in my acceleration as a negative number. And again, 1.38, this one's squared. And this one takes a little bit to plug that into my calculator. That comes out to be 9.5 meters. I'm gonna box it. All right, so again, looking back, the first step was to take the information given and do some trigonometry, because this number here, this 18 meters per second, does not point in the horizontal or the vertical direction, so we don't know what to do with it. So the first thing we did was to build a triangle and break that 18 meters per second into its components. The part that points vertical, the part that points horizontal. And then we were able to do some things that were very similar to what we've done before, but we had an initial velocity in both directions. So we had to incorporate that into our work.